So the dots are supposed to represent, in the case of Harnell, yours are representing your lone pair. I mean, not your lone pair, your valence electron. So if you look on it, hydrogen should have 1. So you should have 1 dot. And your oxygen should have 6.
It says 8. Mine says 8. It says 8 too.
Okay, let me take a look. Okay, so this is the reason why we struggle here. So if you have 8, are 2 of them white?
Yes.
Okay, in that case, those 2 represent, so all the black ones represent valence, and then the white ones represent.
What do they represent? You kind of got cut off.
I said the black ones represent valence, and the white one represents open space.
Oh.
Yeah. Okay. So it's so technically on mine, if you downloaded them, all the ones that are white are representing open space. The ones that are black are valence. Harnell is kind of alternating between the molecules in the packet that they gave. But we'll make it work. Don't worry. We'll make it work. Because we know that there's 6 valence electrons for oxygen. Unless it says O2 minus, then that means that there's 8, right?
So right now we're just cutting them all, yeah.
Yeah. Technically, you should have already had this cut because that was part of your lab 2 weeks ago.
Are we cutting all 4 pages?
Yes, ma'am.
Okay.
Well, cut what you need. That's what because you're only going to need them for the second one.
So Dr. Henry, I have a question. So I'm doing like my Lewis structures. I printed out the forms and I'm like drawing them on there. Now for the actual pictures, do you want me to put them in a Word document, or can I just upload them as because I do them from like my phone?
Yeah, you can upload them. But it would be nice. Ideally, it would be nice if you're doing it from your phone. It'd be nice if you put them all in one document. It makes it easier rather than having to go through 50 documents. And I'm all about, I'm just like an element,
You're an element.
That's right.
Okay.
So can you guys see my screen? So you're going to need them for number 2. So you basically need at least 2 hydrogens, an oxygen. You'll need to be able to have at least 4 oxygens. You'll need nitrogen, a chlorine, which should be easy. And then you'll need hydrogen, nitrogen, and oxygen. Yeah.
Sorry, I missed the beginning. So we're just cutting them out like this, right?
Yep, that is correct. Yep, and what I'd say is just cut out what you need right now, because you need hydrogens. You need how many hydrogens? 3 hydrogens. You need 10 oxygens, 1 chlorine, 1 nitrogen, 1 sulfur. You're making faces, Daisy.
Sorry?
So you're making faces again.
Oh, I'm making faces at my husband over here. Sorry.
Oh, okay.
So I forgot my little things at my work because I kind of try to do my stuff on the DL. So I kind of just, I kind of did the lab with you last week. So I'm just see what I missed a little bit,
Okay. Okay, so let's talk a little bit shop so that it'll kind of help you get through most of the lab. Okay, so we're going to talk a little bit about molecular geometry. We're going to talk about electron pair geometry. And we've already talked about bond polarity. You guys are familiar with that already. Okay, so then we're also going to talk about molecular polarity, okay, and how it plays a part in it. We sort of talked about it. We didn't talk about it too much though. Okay, so I'm going to share a whiteboard with you. And we will start with geometry. Well, let's see.
Hey, Dr. Henry.
Yep.
So you know how you have a PDF like of the geometry figures? Can we use that for our exam?
Yes, you can.
You print it out and use it? Okay.
Yeah, but in that case, those are mine. And so they're all going to be, you're going to have an open spot. So the white dot represents an open spot. The black dot represents valence electrons. Okay. Okay, so let's say we have this. Oops. Okay, so when we talk about electron pair geometry basically means that you're taking into account the electron pairs on the center atom and how it's going to affect things. And initially for this first set, it's not going to make a difference for you. It's going to be the same thing as a molecular geometry. Okay, but this next set, the set that's going to follow this, is going to make a little bit of a difference. Okay, actually quite a bit of a difference. Okay, so the way that we determine geometry is based upon the number of attachments that we have. So we want to count in terms of the electron pair geometry, you count the electron pairs as well as the atoms that are attached. Okay, so in this case, this guy, hydrogen and hydrogen, this guy is going to be linear, right? Because you only have two things attached directly to each other. This here, we have a carbon that's in the center. So it's kind of like this, where you have, this represents an oxygen, this represents an oxygen, and my hand in the middle represents the carbon. So this is a circle is 360 degrees in its angle, and this guy is 180. So it's linear as well. So this guy would also be linear. This guy has 3 attachments. 1, 2, 3. So since it has 3 attachments, my hand represents the carbon in the middle. The white glow stick represents the carbon up top. The 2 sides represents the hydrogens on the side. 1, 2, 3. So this guy would be trigonal, tri meaning for 3. Planar. And it's considered planar because it's all in the same plane, all of the ones. Okay, our next structure, carbon's in the middle, hydrogen, 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 hydrogen. So you have 4 attachments. This is called tetrahedral. Tetra meaning 4. Okay, and this is considered to be, because when we're talking about electron pair geometry, we're talking about electron pairs and atoms that are attached, even though these guys are just talking about the atoms that are attached. Okay, so the molecular geometry would be exactly the same. For the hydrogen gas, that would be linear. For the carbon dioxide, that'll be linear. For the formaldehyde, that is also going to be, that's going to be trigonal planar.
So you're saying basically the electron pair geometry and the molecular are the same?
In this case,
Ah,
and then this is also going to be tetrahedral. Okay. So you got that? Everybody got that so far? Okay. So let me add complications. Okay. So this guy here, it has 4 attachments. The lone pair counts as an attachment. 1, 2, 3, 4. So it's going to be tetrahedral for the electron pair geometry. Now for the molecular geometry, what happens is that you don't see the lone pairs, right? And in this case, you have these three attachments. We have three hydrogens, and my hand represents the nitrogen in the middle. But the lone pair act on the hydrogens. It pushes them down. So they form what we call a pyramid, right? So it'll be bipyramidal. I mean, not bipyramidal, trigonal pyramidal. Trigonal because there's three attachments, or three atoms attached, and pyramidal because it makes a pyramid. Okay, water has, in this case, it has four attachments, 1, 2, 3, 4. So again, it's going to be right tetrahedral.
So you're counting the lone pairs as an attachment as well?
Yep, only for when we talk about the electron pair geometry. That's why we make the distinction.
Okay.
Now,
Dr.
in
Henry,
this
wouldn't
case,
that be a shape, the water, wouldn't that be like the shape name bent or something like that?
that is correct. So that would be for the molecular geometry. It would be bent or angular.
Okay.
Good job. Okay, so in that case, the two lone pairs, right, they're kind of pushing down to make it bend, you know? Okay, and that is your molecular geometry and your electron pair geometry. Yes, got it. But again, this won't be on the test. You're just going to need it for the lab. It won't be on this test, I should say.
So we're not gonna have these type of because in the practice test there's some that asked you what kind of shape it was.
Yeah, I know, but not. I tried to make sure. I'm 99.9% sure I did not put any of those on.
Okay.
If I did, they're extra credit.
Okay, cool. So I was trying to remember how they look.
Okay.
Yes. Not too sweet, but with cream and everything. Cream.
Oh, do I get some? A little coffee to keep you up?
Oh yeah, I've been up since 2
2 a.m.
2 a.m.
Jesus. Whew. You're exhausted, I bet.
Oh yeah, and I got to go back to work again at 2 a.m. tomorrow.
Oh my gosh. I was complaining. I got up at, technically I got up at 5. I was a little late getting up. I would love to say 5 p.m., but that would be a lot. It was 5 a.m.
I would like to say 2 p.m.
Okay, so we're going to use this water for an example here real quick about polarity. Actually, we're going to use this one, and we use carbon dioxide. Start with that one. Okay, so when we talk about polarity, you want to look at two types of polarity. One is called bond polarity, which we've already talked about, right? We talked about it in the lecture. So carbon and oxygen, we know that oxygen, the electrons are going to be going towards the oxygen because it has stronger electronegativity. Okay, So now if you have twins that are exactly the same strength and you're sitting in a wheelie chair, right? Chair that moves, a mobile chair. And each twin is pulling you. They're the exact same strength. Are you going to go anywhere?
No.
No.
No, you're going to stay even. So that's kind of like what's happening here, right? Because the electron is being pulled in both directions. So it's not really going to go anywhere. It's going to kind of stay in the middle. So it's going to have no polarity as a result of that. So the molecule as a whole doesn't have polarity, where each of the bonds have polarity. So bond, it will be polar. We talked about the bond. Polar. But the molecule as a whole, molecular polarity, is nonpolar. Okay. Now, if we looked at water here, so if we looked at the electronegativity between hydrogen and oxygen, so oxygen is more polar, has more electronegativity than hydrogen. So in this case, the electrons are going to be going towards the oxygen in both cases, both sides. Okay, so in this case, it's kind of like you have these two twins next to you, and you actually pull them in. Okay, so you're pulling them. So who's going to be favored, you or them?
You.
Okay. So then this guy has polarity, and it's going towards oxygen. So it's that polar molecule.
Is the bond polar?
Yep. Each of the bonds are polar, yes, because oxygen is stronger in electronegativity, much stronger than hydrogen. So each of the bonds are polar, but the molecule itself is also polar. So molecular polarity is polar. So when it asks you for molecular polarity, you're going to either put polar or non-polar for the molecule. Okay. Let me go back to the carbon dioxide. So we went back to the carbon dioxide. Now you had oxygen over here and oxygen over here, and they were both pulling electrons evenly. So there's a term called symmetry. Symmetry is basically when things are kind of like even, right? Because if we cut ourselves in half, technically we're symmetrical, right? I mean, down the middle, not in half. So right down the middle, we're symmetrical. You have an ear, you have an ear, you have a hand, you have a hand, you have a leg, right?
Ideally.
Okay. Ideally. So if we cut down in the middle of the carbon, right, we're symmetrical in this case, right? It has symmetry. And when we talk about symmetry, we're really talking about kind of like that pull that's associated with that. Okay, so these have equal pulls on both sides. So this molecule is symmetrical. Okay, hydrogen gas is symmetrical. You have hydrogen on both sides. Let me see if I can get to the next page. Let's see.
Would the water bond be symmetrical as well?
Come on. So because they both have pulls going in the same direction, you cut it down the middle, they're going to be symmetrical to each other. So that guy has symmetry. Okay. So if we have, let's see, we had C. O. S. Okay. Would this guy be symmetrical?
No.
So this guy would be asymmetrical. And that's because oxygen has a stronger pull. So you're not getting equal pulls if you split it in half. Okay.
So it could be symmetrical if both of the atoms on either side have equal pulls.
Yeah, if they have
It doesn't
equal
have to be
pulls,
the
yeah.
same. It doesn't have to be like
That's-
oxygen on each side.
No, if
Okay.
they have the same electronegativity on both sides, then it can be symmetrical. But it's rare that you have two things that have the same electronegativity on both sides. So this guy is asymmetrical because these are not equal. Okay.
Got it.
Now, water, we know. And so that's an example where we have polar, but have symmetry. Okay. Sorry. I know you're really feeling that. I shouldn't be yawning, Cassandra. You've had a okay. So does that help with the symmetry and asymmetry and are there any questions?
This is due Friday, right, Dr. Henry?
Yeah, I may give you guys a couple of extra days, depending on how I feel. So,
Those days will be appreciated.
okay.
Yes, please.
Definitely.
Have you guys started looking at the practice test? Oh, I forgot to tell you that. Your practice test is posted already. Your test technically is already posted as well.
Yeah, I took a look at it and I did horrible.
Always that first one, that first trial, you'll get it, the next one. And then now that you've had some more experience, does it help? You're looking back at some of the questions.
Yeah, like it answered a lot of questions today.
Yeah.
The test is due Friday, right?
The test is technically due Friday, yes.
So for this lab, we're just answering questions, right?
Yep. Drawing your Lewis dot structures.
And then is these little it's like on the tip of my tongue, what I would call them.
Your tiles.
Yes.
So those for
is
number
this
two.
Help us out.
Yes, for number two. They're specifically for number two, but they're really just to help you out, right? But I want you to use them for number two.
Okay. And for number two, we'd submit pictures or
That's
draw
right.
it out? Okay.
You submit pictures of them. Yep.
Okie dokie.
See, you're asking all the right questions.
Yes.
Clarissa?
Okay, thank you.
Okay.
No, just kind of looking through the lab because everything you were like writing down, I screenshot to see if it could help me with the lab. But
Yeah.
I'm like looking through it and I'm like, I'm just lost on how to get started.
Yeah, I'm just reading through it too.
Okay. Well, anytime you're ready to ask questions, just let me know.
And you will have office hours on Thursday, yeah?
Yep, definitely.
Okay, cool. I'll probably just try it out by myself then and then probably
Okay.
ask Thursday. Thank you. Have a good night.
Okay. Have a good night. Don't feel rushed. I mean, I have time.
Yeah, I just I feel like I don't know. But yeah.
Okay.
Yeah, Dr. Henry, I'm pretty lost.
Okay. Well, let's see if we can start. Let's see if I can get you guys started, at least on the right track. How about
I'm
Okay,
just
Angie.
confused. Do we have to like tape these to paper to create the?
No, to each other, right? Really just to each other. And you don't have to tape
Oh.
them, you just have to put them in the form. So like, for instance, we're making water, right? So let me put my other one. So if I was making water, these are like set up for their open spaces. They're mine, so in this case, right, I put my oh, man. Okay, so can you guys let me stop sharing my screen now, and then I'll put myself in the middle. Okay, so in this case, my oxygen, the black represents valence electrons. The white represents open spots. So I'd have my oxygen, my hydrogen there, and then my other hydrogen here. And so then I take a picture of it looking like that. Okay. And then if you count it, that's, here's the one that the hydrogen is giving. So that's actually the wrong spot here. Sorry, right there. Okay. So then the hydrogen is providing one. So that's 2, 4, 6, 8 around that hydrogen, around that oxygen, and then there's 2 around this hydrogen, and that's 2 around this hydrogen.
Oh, because you said it's always trying to be the 8, right?
That's right, octet. Yep.
Okay. And so the white dot is technically
Yeah, that's the one that the hydrogen is providing. Yep.
Oh, okay,
Yeah.
gotcha.
Yeah, we have to get them a little more uniform. My sheets from Belinga are different than from yours, and yours is partially the way mine is, but not completely. So, because your oxygen has 8 around them, do they not?
Yeah, they have the little number on them.
Yeah, and then they have 8 dots total, with 2 of them being white.
Not all of them though, right? Just some of them?
Yeah, it's really screwed up. We've
I was
got to
gonna
get them a
say,
little more.
just some of them have 8 and some have 6.
Yeah. So does the one that have 8 around them, do they have 2 minus next to it? Because that's what they should have done.
No, like, let me show you. I only have one with 8. I don't know if you guys also have just one. Yeah. all the
Yeah,
other
so
ones-
in the case of the ones that have 6, yeah, so that one has 6, right? So in that case, that one worked perfect because you're getting 2 dots from your hydrogens. Each of your hydrogens, you can't, it's really hard to see, but they have a dot on the top, right?
Gotcha. So it'd be like,
So
I don't see any with 8.
you don't have
But
any
I
with
could
8?
be blind.
So all yours has 6, then that's perfect then. Then you use the one, it'll work out. So then the dots in your case all mean that they're valence electrons. They're just showing you where they're going to be matching up. Does that make sense?
Okay, because some are, the
Yeah.
dots are in the different
Perfect.
area.
Yep, that's right. Yeah, they should, like hydrogen, nitrogen has 5, right? And they should have, they're gonna have them located differently depending on who they're bonding. Right, so like for instance, if it was bonding with, if I was making carbon dioxide, right? So then I'd have 2
Yeah.
on one side, 2 on the other side that are gonna be contributing.
so for the first part of it, the 1 through 5, they identify the central atom down. Do we have to include all that in the report or just the actual questions that you asked?
No, you wanna put all of that, because that's part of the report. So if you identify, you have to tell me what the center atom is, then you also have to tell me, because if you, the question, if I remember correctly, the table, you want to include the table. That's part of it.
Oh, okay, okay.
Yeah. So you want to, basically you want to fill in all of it.
Okay.
Yep. So does that kind of help explain it, Angie and Christine?
Yeah, I'm just still getting confused about the whole 8 but 6 dots on the tile thing.
Yeah, well, because 8 represents where it's located, the number.
Oh, and there's 6
Yeah.
valence electrons.
That's correct. Yes.
Okay. Well, I was getting confused with the colors because I'm like, there's 4 black, but there's 6 valence electrons.
Yeah. Yeah. Well, yeah. We're working out those details, you know.
Okay.
Process, figuring that out. So, but our next one will be all worked out, you know. So.
Okay. I don't know if
All
I'll be
right.
able to catch it, but I'll try.
Yeah, we'll try to figure it out. Thank you, Dr. Henry.
Yeah,
No problem.
thank you.
You've been
You guys
here
have a
all
good
day. Good night. Rest up.
Night.
Bye. Bye.